Hello students, today we're going to talk about implicit differentiation. Our goals for today are to find the derivatives using implicit differentiation and then to find slopes of tangents using implicit differentiation. Implicit differentiation. What is implicit differentiation? The chain rule, we're going to use it in order to find implicit differentiation, and it's going to be a very powerful tool in this case. The reason why the chain rule is useful is because it is often easier to write down some relationship between x and y than it is to write down a formula that gives the value of y in terms of x. For example, sometimes when we have an equation that relates x and y, we can easily solve for y in order to be able to differentiate that. Like the example x minus 4 equals 2y, we can easily solve for y and then differentiate. But it is not the case if we have a complicated equation like x cubed plus y cubed is equal to 8xy. But luckily, we don't have to solve for y in order to be able to differentiate an equation. Rather than solving for y, we can differentiate in place using the chain rule, assuming y is a function of x. Remember that the operating notation, the differentiation of y with respect to x, I am going to read it dy over dx because it's more convenient that way, can also be read as the differentiation with respect to x of y, where d over dx means take the derivative of what follows with respect to x. For example, if we want to find the derivative with respect to x of x to the second power, the answer is 2x. We know that. The derivative with respect to x of y is basically dy over dx. Now let's combine the chain rule with the operating notation. Let's find d over dx of y to the third power, or y cubed. In this case, I can write this down as d over dx of y all to the third power. And I can regard this as an amount raised to the third power, and then I can differentiate this using the chain rule. So if I'm going to use the chain rule, I have parentheses raised to some power. That means I will differentiate it this way. I'm going to say this is equal to, the power comes down, and then the parentheses remain intact, and then I will take 1 away from 3, so I will have 2 times, remember I'm using the chain rule in this case, the derivative of what's inside. So the derivative of that. Now I'm going to put y back right here. So I will have 3y to the second power times y prime, or the derivative of y. I know the derivative of y with respect to x is dy over dx. So this boils down to 3y to the second power times dy over dx. I'm going to use this idea in order to solve the rest of the examples using implicit differentiation. Let's try another function that we already know how to differentiate. Let's say we want to find the derivative with respect to x of x to the third power. Now, if you ask me that, I know the answer, which is going to be 3x squared. Let me do it using the chain rule. So I'm going to rewrite it as d over dx of whatever inside the parentheses raised to the third power. Now I'm going to deal with this amount as a parenthesis, so I'm going to use the chain rule to differentiate that. To differentiate that, I'm going to say this is equal to 3 times whatever inside the parentheses is, and then 3 minus 1 is 2 times the derivative of what's inside the parentheses. So now this is equal to 3 times what's inside the parentheses is x to the second power times, and then the derivative of x, which is dx over dx. Now the derivative of x with respect to x is equal to 1, as we expected. So the final answer is going to be 3x to the second power. Let's look at more examples. Let's find dy over dx, or the derivative of y with respect to x, for x cubed plus y cubed equals xy. Now in this case, we can't solve for y easily, so we're going to differentiate in place, and we're going to use implicit differentiation. In this case, I will take the derivative for each term of these terms. So I will rewrite this as d over dx of x to the third power plus d over dx of y to the third power is equal to d over dx of xy. The derivative of the first term, the derivative of the second term, the derivative of the third term. Now I'm going to treat each one of these as parentheses, and then I'm going to differentiate using the chain rule. So if I differentiate using the chain rule, this will turn into d over dx of x to the third power, parentheses, plus d over dx of y to the third power equals d over dx of xy. Now I will differentiate this regarding it as parentheses, and I'm going to use the chain rule in this case. So I will have 3 times x raised to the second power times the derivative of the amount inside of these parentheses, so dx over dx, plus the derivative of the second term is going to be 3 times y to the second power times the derivative of what's inside the parentheses, which is dy over dx, equals, in this case I have a multiplication, so I'm going to use the product rule in this case. So I'm going to say the derivative of the first one times the second one plus the first one times the derivative of the second one. So here's a function and here's another function. The derivative of the first function times the second function plus the first function times the derivative of the second function. Now I'm going to simplify. I know that dx over dx, the derivative of x with respect to x, is equal to 1. So I'm going to replace that with 1, and I'm going to make this expression a little bit neater. So I will have 3x to the second power times 1. I'm not going to write it down, plus 3y to the second power times dy over dx equals dx over dx is 1. So I will have y plus x dy over dx. Now remember, I want to solve for dy over dx, so I will need to gather all of the terms that have dy over dx to one side and kick all of the terms that don't have it to the other side. So I will have 3y to the second power dy over dx minus x dy over dx is equal to y minus 3x squared. Now I'm going to take dy over dx out as a common factor. I have it here and I have it here. I'm going to pull it out as a common factor. So I will have dy over dx times what's remaining. I'm going to have 3y to the second power minus x on this side equals y minus 3x squared. Now, again, I want to solve for dy over dx, so I'm going to divide both sides by the amount between the brackets. So I will have dy over dx is equal to y minus 3x squared over 3y squared minus x. And that is the final answer. And I found dy over dx without needing to solve for y. And this is how we do implicit differentiation. Here is another example. We want to find dy over dx of y equals the cube root of x squared plus 5x plus 4. Now, if you're like me, I don't like radicals. I don't like radicals at all. So in order to simplify this, I'm going to remove that radical. And that will give me, if I cube this side, I cube that side, then the cube is going to go with the radical, and then I will have y cubed is equal to x squared plus 5x plus 4. Now, luckily, I know how to differentiate this using implicit differentiation. So I'm going to take the derivative for both sides. So I will find the derivative dy over dx of y cubed is equal to d over dx of x squared plus 5x plus 4. Now I'm going to differentiate using the chain rule again. Regard this as parentheses. I'm going to say this is equal to 3 and then y to the second power times what's inside of the parentheses, the differentiation of what's inside the parentheses, dy over dx is equal to the differentiation of addition of terms is the addition of the differentiation of those terms. So I'm going to differentiate each of these terms by itself. Again, I'm going to regard each one of these as parentheses and use the chain rule. So I will have 2x to the first power times dx over dx plus the 5 comes out using the derivative rules, and then the differentiation of x is 1 times dx over dx, and then plus the derivative of a constant is 0. I know that dx over dx is equal to 1, so I'm going to replace that. I will have 3y squared is equal to 2x plus 5. Sorry, I forgot dy over dx right here, so I'm going to put it here, dy over dx. It's a multiplication. Okay. Now, I want to solve for dy over dx, so I'm going to divide both sides by 3y squared. So I will have dy over dx is equal to 2x plus 5 over 3y squared. But notice here how I have y in my derivative. I don't want that to happen. I know that y is equal to the cube root of x squared plus 5x plus 4. So I can remove this y and replace it with its value. So that's what I will do. Again, I'm going to write it down. Y is equal to the cube root of x squared plus 5x plus 4. So all I'm going to do, I'm going to replace the value of y back into this equation. So I will have dy over dx is equal to 2x plus 5 over 3, and then I'm going to put that in here, all to the second power. I'm going to remove the y, replace it with a blank, and then replace that blank with the value of y, which is the cube root of x squared plus 5x plus 4. Now, if I would have done this the old-fashioned way, I would have reached the same value for the derivative of this function, but this method is way faster than the previous one that we have learned. So that's a benefit that we can reap from implicit differentiation. Let's find the slope of a tangent line using implicit differentiation, which is one of the applications. We're going to find the slope of the tangent to the graph x squared plus y squared minus 9 equals to 0 at square root of 5 and 2. So we know that the slope of the tangent line is equal to the derivative, meaning we need to find dy over dx. But y in this case is kind of hard to solve for. So we're going to use implicit differentiation. So I'm going to say I will find the derivative for the left-hand side and the right-hand side. I'm going to say d over dx of x squared plus y squared minus 9 is equal to d over dx of 0. then I know that the derivative of addition of functions or addition of terms is going to be equal to the derivative of each one of these. So I'm going to say d over dx of x squared plus d over dx of y squared minus d over dx of 9 is equal to the derivative of 0 is 0. Now I will use the chain rule again, making sure that I will treat y as a function of x. So here it goes. I'm going to say this is 2x to the first power, and then I know I have to differentiate x with respect to x, but I know that is equal to 1, so I'm not going to write it down. Plus the derivative of y squared is basically 2y, but I need to differentiate y with respect to x, so dy over dx. Minus the derivative of a constant is 0 is equal to 0. Now I will continue on that example. So I had 2x plus 2y times dy over dx is equal to 0. Now I want to solve for dy over dx because dy over dx is basically the slope of the tangent line. So to solve for that, I will need to take this amount to the other side. I'm going to subtract 2x from both sides of the equation. So I will have 2y dy over dx is equal to negative 2x. Now I want to solve for dy over dx, so I'm going to divide both sides by 2y. I will have dy over dx is equal to negative 2x over 2y, which is essentially equal to negative x over y when I cancel the 2's together. So that is basically the slope. The slope is negative x over y. Now I want to find the slope at x is equal to square root of 5 and y is equal to 2. So in this case, the slope of the tangent line m is equal to negative x, which is negative square root of 5, over y, which is 2. And that is the slope of the tangent line.